So let's begin with the general introduction to Finn. So the Finn effort actually began back at FPGA. So this conference 4 years ago, where we had our first results published and the first proof of concept of the Finn framework. At that time, we implemented fully binarized neural networks for MNIST and CIFAR10 classification. Since then, Finn has evolved significantly. We have 3 full-time researchers in my team working on this over the last 4 years, in which the framework not only matured, but also much more functionality has been developed and released, while also the community has started to pick up. The mission of Finn today is to provide tools and platforms for the creation of high-throughput, ultra-low latency DNN compute architectures. Finn provides an end-to-end flow from neural network to hardware, where users can easily create specialized hardware architectures on an FPGA and benefit from custom architectures and custom precision. Finally, Finn is designed as an open source from the ground up to provide transparency and flexibility to adapt to end users' applications, which is very important in the machine learning space where algorithms are heavily in flux. Finn leverages 2 key concepts for accelerating neural networks with FPGAs. The first one is streaming data flow or spatial architectures, and the second one shown on the right-hand side is custom precision, where we present weights and activations in neural networks with just a few bits. And we will explain these 2 concepts in greater detail in the coming slides. Let's begin with the data flow architectures. And the best way to understand is perhaps to contrast it to other approaches. So here we distinguish between 2 forms of architectures. We have the more generic matrix of processing engine, or MPE for short, on the left, and data flow architectures on the right. Matrix of processing engine is probably the most popular used approach. This is what's used by GPUs and many of the ASICs. And in general term, this architecture consists of a matrix of processing engines, which are shown here in red, whereby a processing engine can be as simple as a multiply accumulate, a vector processor, or a ReLI-W processor. And then, of course, we have some form of memory subsystem, which I was too lazy to draw, and perhaps we can ignore it for the sake of this tutorial. Of course, this is a highly simplified view of the world, but it helps to get the concepts across. So this architecture performs what we call a layer-by-layer compute. Inputs to be processed are loaded onto the device. Then I schedule the compute of my first layer. I execute it, buffer the results. Then I schedule my next layer, and so on and so forth. So it's kind of an iterative layer-by-layer compute. They're customized for machine learning in general in regards to the type of operations and ALUs they support. For example, lots of multiply accumulates. These architectures achieve typical performance up to tens of thousands of requests per second. They provide the necessary flexibility for the ASICs, as you can basically run any DNN on this as long as it uses only operations that are supported in the hardware architecture. And this is popular, this approach, within the computer vision and the speech application context using large DNNs. Now, on the right-hand side, we show customized data flow architectures, which basically customize or adapt the hardware architectures to the specifics of the topology. So, for example, you could have a ResNet-50 accelerator. All layers have here dedicated hardware compute resources in the device, whereby the compute resources are proportional to the compute requirements in each of the layers to balance the throughput through the design. And the inputs are then just streamed through the architecture. It's like a pipeline. So this specialization brings a number of advantages. Efficiency, we only instantiate what's needed. Latency, as we don't need to buffer before and after layers. And finally, higher throughput. This architecture can scale to hundreds of millions of requests per second, as we will show you. So these architectures are completely specialized for specific topologies. So if you change the topology, you need a different architecture. But that's okay, because we can offer the flexibility in FPGAs through reconfiguration. ASICs don't make sense here. So applications are here still TBD. But from our research, we can see strong promise, for example, in networking, material science, particle physics, and other domains using typically lower complexity DNNs. So a specific advantage of the data flow architecture is that I can scale them to meet performance or resource requirements. So I'll show this on this very simplistic example of a 2-layer DNN accelerator. So first of all, I can shrink the resources footprint by removing compute resources from each layer proportionally. And conversely, I can go the other way and I can increase the throughput. So if I have enough resources in my device, I can just keep adding more and more compute to each layer until eventually every single neuron has its dedicated hardware resource, at which stage my architecture will run at maximum speed and classify at clock rate. So at 200 megahertz, I will get 200 million requests per second. So this is how I can achieve extreme high throughput. So when completely unfolded, we talk about fold factor of 1. The middle one is a fold 10, and the one to the far right, fold 1000. So fold factor is basically proportional to the achieved throughput. Upshot here is that the architecture can scale performance and resources to meet the application requirements. And if my resources allow it, we can completely unfold it to create a circuit that actually inferences at clock speed. So, and you'll learn in this tutorial how to do this. The other popular trick we can exploit with FPGA devices is reducing data type precision. And you might be well familiar with this already. There are lots of publications on this. And this is the key to scaling throughput in DNNs towards high throughput requirements. The idea is basically to reduce the data types for weights and activations during training as much as possible. While I can still achieve sufficient accuracy for my application. So you'll experience in the hands-on part again how to reduce the precision during training. So there are a number of benefits coming from this. First of all, if I reduce my multiply accumulate from operating at 8-bit 8-bit to 1-bit 1-bit, the hardware footprint of my multiply accumulate shrinks by roughly speaking 70x. So we've benchmarked this, by the way, for high-level synthesis and RTL, as you can see in the chart on the right-hand side. And when I shrink my compute operator, that means I can instantiate many more of that type. And as DNNs are incredibly parallel, this then basically translates into performance scalability. Now, secondly, it reduces my memory footprint for the weights in my DNN. So let's consider ResNet 50, which has 25 million weights. If I store them at 32 bits, then I need over 100 megabytes. If I store instead just 1 bit per operator, then I only need 3 megabytes, which is something I can store on chip and avoid any potential memory bottlenecks. So finally, it also saves power in 2 ways. Firstly, by staying on chip, I save significant power. See the table here below. This was published at ISFPGA a few years ago for 40 nanometer ASICs. The same applies to FPGAs. Unfortunately, nobody has ever made this table for me. So if someone out there has spare cycles, please do it for all of our sakes. You'll get lots of citations from this. So coming back to the point of saving energy by not having to go to external memory, check it out. DRAM read is 640 picojoules, SRAM read is 5 picojoules. So there is a significant power savings in this. Secondly, reduced precision operators inherently require less energy. For example, compare the 32-bit add to the 8-bit add, there is a factor of 3 in between. So there are 3 massive benefits that I get from reducing precision, namely performance or resources, memory, and power. And this is what we exploit with Finn. So let me drill in a bit deeper into the granularity of customizing arithmetic. So in the context of MPEs, let's say I customize my processing engines to operate with int8. As I'm doing a layer-by-layer compute, and I don't know where my compute actually ends up on that matrix of processing engines, the implication is that all weights and activations over all layers have to be int8. In the context of data flow architectures, I have much more liberties, as every layer has dedicated compute resources with different precision support if required. So I can have different positions not only between weights and activations, but also between the layers. And while this again is simplifying the actual truth, the general point is that with data flow architectures, you get a much finer granularity in customization, which allows to exploit customized arithmetic to a much larger degree than you can with MPEs. So to make things a bit more concrete, let's take a look at a few particular examples. So the first example, it's a fairly old one, shows a CFAR10 classification on PYNQ board offering 3000 frames per second at 2.5 watts with 1 millisecond latency. So this showcases that you can do big computer vision tasks at very low power envelopes. The second shown here on the right is your popular computer vision DNN. For example, ResNet 50 and MobileNet V1 we have for ImageNet classification. So we have single and multi-node implementations on Alveo boards for those using the Xilinx academic compute clusters, or XACC for short. And you might wonder what those are, and I'll tell you in a little bit later more about this. So as examples, I have here 2-node Alveo U280 delivering 5.9 thousand frames per second at 2.2 milliseconds for MobileNet V1, which is highly competitive, and 3.1 thousand frames per second for ResNet 50 single node on a U250 with 1.7 millisecond latency. Our most recent example is one from network intrusion detection in wired and wireless telecommunication systems. And you'll actually work with a version of this in the hands-on part later on. So here's a block diagram of your typical system, which consists of a packet processing pipeline with a network interface on the input and the output. Packets come in, they go through the packet parsing block, which feeds into the traffic classification block. This is where actually the DNN sits, followed by the packet filter, which will either drop or pass the packet. So DNNs are increasingly popular here because of the increased accuracy that a DNN will give you, and because it avoids feature engineering, which is an ongoing battle in the context of cybersecurity. So you get new forms of malicious traffic emerging all the time, and instead of figuring out what the role in the network intrusion detection system needs to look like, I train my DNN on latest traffic traces. In regards to throughput requirements, they're extremely high here. So at 100 gigabits per second, assuming a minimum packet size of 64 bytes, it would require a throughput of 150 million requests per second. Also note this application is latency sensitive, as I need to buffer all my traffic here while I'm deciding what to do with the packets. So it's like drinking from a fire hose. 1 millisecond of 100 gigabit per second traffic is 100 megabit. That's a huge amount that you have to buffer. So let's take a look at the results for network intrusion detection systems. So we've considered 3 implementations here. One is a matrix of processing engine. For this, we use Vitis AI, and 2 of them are fin data flow architectures. Fold 1, that's the fully unrolled one, dedicated hardware per neuron, and 1 is folded 8 times. All of these are implemented on the same FPGA, which is an UltraScale Plus 60 nanometer technology node. So all of the implementations that we have execute the same DNN, which is a so-called multi-layer perceptron, relatively small DNN, which requires 92,000 operations to process a single input. Vitis AI uses 8-bit position. Fin uses reduced position with 2 bits per data type. And in terms of accuracy, the 8-bit implementation on Vitis AI is around 92%. The Fin implementation is 91.9%, so pretty close in accuracy. So let's compare the performance now. So Vitis AI delivers 22,000 requests per second, while with Fin, depending on the folding factor, we get between 25 and 300 million requests per second. So it's over 1000x faster. And if you recall, this rate, 300 million requests per second, meets the 100 gig line rate requirement. And the benefit here comes mostly from the reduced position. Also, the latency reduction is huge, right? So Vitis AI has 26 microseconds. This was measured, by the way, with ChipScope, right? So we've excluded all data movement overheads here. FinFold 8 needs only 160 nanoseconds, and the fully unrolled runs even at 80 nanoseconds. And the benefit here comes from the data flow architecture, which avoids the buffering between the layers. So huge reduction here. So now you might wonder, well, what's the hardware resource implications of this? So I've broken this into compute and memory resources. In regards to compute, the Fin implementations are slightly smaller, right? So we go from 122,000 LUTs and over 1,000 DSPs down to 44,000 LUTs. The Fold 1 is, again, a little bit higher in resources because I had more compute resources to the side. That goes up to 69,000 lookup tables. whereby the actual size depends on the actually trained weights. As when you unfold one, every neuron has dedicated hardware, the weights actually get absorbed into the logic, and synaptic connections where the weight is 0 will get pruned during synthesis. So it's a very nice effect. Memory is a great story too. Gets massively reduced thanks to reduced position, and the best thing happens again when I fully unroll. That's when the memory actually evaporates, because it gets fully absorbed into the logic. No BRAMs and no URAMs are needed. So overall, we get 1000x performance improvement over matrix of processing engines at less resources, achieving the 100 gig line rate requirements through data flow and reduced precision. But bear in mind, this depends on your application. It's only if your application is actually amenable to this form of optimizations. But if it does, it's great. So hopefully by now you're excited about what you can achieve with Finn and understand the key concepts. So let's talk now about the framework and how you can create these designs. So Finn consists of an end-to-end flow from trained DNN all the way to hardware, and it has 3 components. The first component is brevitas, which is a machine learning library based on PyTorch, which is very popular in the machine learning community, that allows you to train or even learn reduced precision DNN. It contains a library of quantized versions of standard layers and a selection of pre-trained examples. brevitas supports exports a trained neural network into the Finn compiler. So the second component is then the Finn compiler, which creates the customized hardware architecture via code-generated HLS code. The Finn compiler produces a DNN hardware IP, which can be embedded into your application. And the third part is the deployment flow. We have a selection of infrastructure design supported, mostly built on PYNQ, works on a number of selected of embedded and Alveo platforms, including the aforementioned XACC. So let's discuss these components now in more detail, beginning with brevitas. So normally, if you try to directly convert a floating point network into a few-bit integer network through direct quantization, you would experience some accuracy loss on the target task because you're in essence deploying a different neural network compared to the one you've actually trained. So the solution to this is what is called quantization-aware training, and this is what brevitas implements. It is essentially a library of PyTorch layers with extra parameters to describe your quantization scheme during training. And this allows you to train a quantized neural network for much better accuracy results. So brevitas is quite flexible in terms of the quantized training capabilities. For instance, you can set the precision for weights and activations manually, or let it be learned using backpropagation. Scaling factors are important for DNNs, and brevitas lets you apply them with different granularities and strategies. For example, you can set the scope of a scaling factor to be tensor or layer wide. You can quantize weights, activations, and accumulators separately. And last but not least, when you've trained your DNN, you can export the DNN to the Finn compiler via ONNX. ONNX is an open source interchange format which uses a protobuf description to represent DNNs. brevitas is open source on GitHub, available on the link you see below and that I'm circling here with the pointer. The next component is the Finn compiler. So it gets the model from brevitas in the previously mentioned ONNX representation. By the way, we use ONNX not only as input for the Finn compiler, but also as intermediate representation during the individual steps of the Finn compiler, or IR for short. The Finn compiler itself is a library consisting of graph transformations which operate on ONNX IR of the DNN. This eventually generates a synthesizable description of each layer in high-level synthesis, and from this the user can generate IP blocks for each layer with axis stream inputs and outputs. Using the axis stream interfaces, the design can then be easily stitched together using Vivado API, and you can create a stitched DNN accelerator IP, which is the output of the Finn compiler. So just drilling a little bit more into these graph transformations. So every step in the Finn compiler is a graph transformation on the ONNX IR. And let me explain in more detail what exactly that is. So it is a step in the Finn compiler is a Python function that takes as input a graph, looks for a specific pattern, and changes the graph in a particular way. Afterwards, the changed graph is returned back to the Finn flow. So for example, on the left-hand side, we replace this pattern of nodes in the red circle in the graph on the left-hand side with the red circle in the middle. This particular transformation is actually called streamlining and is very important in the Finn context. Optimizations such as streamlining, as well as lowering convolutions to matrix multiplications, which is the example showing on the right-hand side, are all examples of these graph transformations. So the Finn compiler involves conceptually 3 steps. First step is import the ONNX description, optimization, and conversions. Second step is adjusting the performance, remember the folding factors. And third step is IP generation. We'll give a simplified overview here. In practice, each one of these steps is actually one or more compiler passes that are invoked by Python commands. Now let's have a closer look at how each step operates and what's involved. So the first step, drilled into more detail, it imports the trained neural network, optimizes it, and converts it into a HLS description. So you can see here an example of such a HLS description on the slide. If you're not familiar with high-level synthesis, think of it as a way of expressing designs in C++ that can be synthesized into circuits. And by the way, we're actually not generating arbitrary HLS code, but rather we're generating calls to our pre-optimized HLS C++ library of common neural network layers, which we'll explain a bit more in the next slide. So in this example, you can see some calls to instantiate fully connected layers using streams as inputs and outputs. So you see here a streaming FC layer, and here you see the inputs and outputs in inter 0, inter 1, they're all defined as HLS streams. Also note the binary in the layer function calls. Our C++ library supports arbitrary precision data types with templates, so we can mix and match weights and activation positions for different layers as desired. So this description that you have here then can be synthesized in RTL. So our HLS library provides more than 10 common DNN layers. The defining features of finn-hlslib are shown here on the example of the matrix vector threshold unit, or MVTU for short. The MVTU is a key component of our library and key part of both convolutional and fully connected layers. Key features are: the unit has a streaming interface, which makes it easy to compose larger systems and supports low latency. It is highly customizable through the C++ template, which allows user-specific data types on both inputs and outputs. And finally, we have parameters for defining the degree of parallelism to control the resource footprint or the throughput. So there's 2 parameters involved in this. The first one is number of PEs, which determines the number of output channels I can compute in parallel. And the second one are the SIMD lanes, which determines how many product terms I can compute in parallel. So that allows me to scale throughput/resources, which is shown in the next step here. So input and output is the HLS design, and we can adjust the design such that we can trade off more FPGA resources for more throughput, or conversely save on the resources. And we're doing this again, just to remind you, by adjusting PEs and SIMD width, which are inputs to the template classes. Okay, so once we've adjusted the performance of the network to our needs, we can go ahead and run the IP generation step. This produces Verilog packaged as a series of IP blocks for Vivado IPI for easier system integration. In the figure here, you can see an example of a generated IP design. This is the final step in the Finn compiler tool flow. With this, our accelerator is then ready for integration into a larger system. Now, coming to the third part is the deployment flow. We support deployment mostly with PYNQ. PYNQ offers interfacing the accelerator directly at Python level, as is shown in the example code here, which makes it really easy to use, in particular for users which perhaps are not as FPGA savvy as yourself. So first we instantiate the accelerator here. Then we create an input. In this case is a dummy NumPy input tensor with the right dimensions. Note that we operate here on NumPy tensors. This is the common way within the machine learning community. And by the way, internally, we use PYNQ DMA drivers to read-write NumPy arrays and convert them into I/O streams. And then we call the actual or execute the actual accelerator. Overall, this should be pretty easy to use, even if you're not a hardware person. Now, we also provide free infrastructure for experimentation in form of the Xilinx academic compute clusters. This is, by the way, not just for Finn. They can be used for anything. There are 4 worldwide, 2 in the US, 1 in Singapore, and 1 in Switzerland, and they're completely free to use and specifically intended as an enabler for the research community. So they're different from common infrastructures such as AWS and Nimbix because they are much more flexible. For example, you can directly network FPGAs to each other, or you can implement different shells. And as such, this infrastructure is much better suited for carrying out research. To give you an example of one of these clusters, the one at ETH Zurich looks something like this, has 5 servers stuffed with a total of 10 high-end FPGAs, which are all interconnected together with the host to a 100 gig Ethernet network. If you'd like access, please be in touch. These clusters are intended for you to use freely to advance your research. So give us a shout if you'd like to have access. So in regards to status, after multiple years of development effort, we have many example designs available on GitHub with increasing application feature and platform support. It's still active with ongoing development by us and Xilinx Research, but also increasing community engagement. And Saeed will tell you a lot more about this in a later part. So we have plenty of training material available here. More tutorials are coming. In particular, I just want to say we're really sorry again if you didn't get a spot in the hands-on part. We will run the next one in a month and you'll be on the top of our list. And there are also a number of universities using Finn meanwhile for teaching, most notably perhaps Stanford University already 2 years in a row and many more coming. And our main focus right now is we're looking to build up community, applications, and functionality. So if you're interested, let us know. We'd love to hear from you. And with that, we come to the end of the first part already. So let me hand over to Yaman himself for a tour of the repositories.
Thank you, Michele. Just take over the screen sharing here. So once again, good morning, good afternoon. I hope you can hear me clearly. I'm Yaman. I'm here to give you a quick tour of the Finn repositories to sort of give you a little bit more of a concrete idea in terms of where do you find what information and how is this whole thing that Michele presented to us structured. Just bring up the laser pointer and off we go. So the Finn project has grown significantly over time and it has a lot of parts. So in this section, I want to give you this quick practical tour of the various bits and pieces of the project. And hopefully you'll get a better idea of where do you find what information in all of this. In general, the go-to place for all things Finn is our project landing page on this URL over here that I'm highlighting with the pointer. This acts as a portal and has links to all of the various Finn repositories that I'm going to show today. It also houses the Finn blog, where we announce the latest developments, as well as publications, videos, and various other resources. So it's well worth a visit. Now, this diagram here on the slide gives you an overview of the Finn software stack as it exists today. So as I mentioned, it's grown into a significantly sized project, and we're trying to facilitate modularity and reuse. And in order to do that, we've been trying to restructure it as a set of software components. So each of the boxes that you see here is a separate repository or software module by itself. At the top of the stack, we have our library of pre-built Finn examples. In the middle, we have the Finn compiler itself. And in turn, the compiler is built on top of 3 pillars. Brevitas, which is our quantization-aware training library in PyTorch, acting as the front end to the compiler. finn-hlslib, which is our Vivado HLS operator library of neural network components. And FinnBase, which provides our core compiler infrastructure together with ONNX and ONNX runtime. Now, let's have a deeper look at each of those components, starting with Finn examples at the top. As the name implies, this repository houses example dataflow accelerators built with Finn, and you can find it on GitHub at this URL here. Here, you'll find pre-built bit files targeting several image classification datasets and a variety of PYNQs on Zinc and Alveo platforms. Each example also comes with a PYNQ Python driver, as Michaela mentioned, and a Jupyter notebook demonstrating how to use it. So if you're just starting out as a new Fin user, this is probably the best place to begin, as you can simply pip install the repo on your board and run these examples. Furthermore, if you actually want to customize these examples or build your own based on the existing ones, the repo also contains the scripts to actually build everything from scratch using the Fin compiler. We'll be expanding this repo with more examples over time. You can look forward to, in the short to medium term, to the toolflow example for ResNet 50. The ResNet 50 bit files themselves we already have on a different repo here, as well as some novel DNNs for speech recognition and keyword spotting. And last but not least for this slide, I want to say we'd love to have community contributions to this repo that showcase the cool dataflow accelerators that you have built with Fin. Next up on the stack, we have the Fin compiler repository itself, which is one of the most critical components of the stack. So the Fin compiler toolflow, the Fin compiler repository houses the toolflow that Michaela mentioned that actually provides the full build automation going from ONNX all the way down to a bit file or Vivado API design. Here, you'll also find a full Docker environment that pulls in the correct versions of all dependencies of the software stack. So in this way, this repo has the glue that's bringing all the various components in that software stack figure that I showed you together. In terms of content, all the machinery that provide the various bits and pieces and features for dataflow accelerator generation reside in this repo. This includes, first and foremost, a large library of graph transformations that Michaela mentioned, ranging from streamlining to conversion to HLS operations, to code generation, to stitching everything together in Vivado IP integrator. There's also a library of custom ONNX ops that correspond to finn-hlslib components, which we'll come to in a second. And these provide the code generation and verification functionality for our HLS custom ops. And finally, we have Jupyter Notebook tutorials that cover a range of topics from basics to worked end-to-end examples. This actually also includes the hands-on material for today's part, if you haven't been able to get a spot. Overall, I'd say this repo is one of the larger ones in the stack, and there's lots and lots and lots more there to explore. And you can find the repo itself, as well as the Fin documentation on these links over here. Next up, we have brevitas, which serves as the front end to the Fin compiler. Brevitas is a quantization-aware training library for PyTorch, and it deserves a full tutorial of its own, but I'll try to just cover the aspects that are most related to Fin here. So, mentioned quantization-aware training. Quantization-aware training allows you to train neural networks with quantized weights and activations, which is essential for getting good accuracy with less than 8 bits. The way the user sets this up is by using quantized versions of standard PyTorch layers. So for instance, you'd be replacing your conv2d layers with quant-conv2d layers that are actually coming from brevitas, and this then specifying the desired quantization. On that aspect, when it comes to specifying the quantization itself, brevitas is quite flexible. It lets you do things like mixed precision layers whose bit widths for weights and activations can be different between layers, and they can be set manually or, for instance, learned with backpropagation. There's a number of example quantized models and training scripts available across several domains, ranging from image classification to speech to text to speech. And here I want to point out another opportunity to broaden your impact on the community by actually contributing quantized DNN models to this repo. And finally, I want to add that besides Fin, there are other things that brevitas can actually target. So there is work in progress to export different flavors of ONNX for different backends, including the Vitis AI DPUs from Xilinx and standard 8-bit quantized ONNX that runs with, for instance, ONNX runtime. Next up, we have finn-hlslib, which is our operator library. Now, Michaela already covered, again, the key parts of this, and I'm just going to briefly recap the software structure bits of it here. What will you find in this repo? In this repo, you'll find templated, optimized Vivado HLS C++ code that implements more than 10 common DNN layers. And here, I'll take a moment to highlight that there's room for plenty more community contributions there in terms of new layers. Our HLS library is actually one of the most externally used parts of the Fin project. So if you actually contribute to the finn-hlslib, there's a good chance that what you contributed will end up being part of some great NN accelerator that ends up winning best paper awards at F conferences and so on. Coming back to the specifics of finn-hlslib, there is a lot of configurability built into the components via template arguments. So here you can customize the input, weight, and output data types and precision, the amount of parallelism along different loop axes, and the particular type of FPGA resources that you want to use for particular layers. Another defining feature here is the interfaces. Almost every interface on these components in finn-hlslib is an axis stream, which makes them easy to compose together into a layer pipeline, which is something we do in Finn. Finally, moving on to the compiler infrastructure side of things, we have the Finn base repo, which I'll touch on briefly. To develop the Finn compiler, we've had to build a bunch of infrastructure that lets us manipulate and verify custom ONNX graphs. And this is what we open sourced in Finn base. The important thing to emphasize here is the following. This repo is quite general. So Finn depends on Finn base, but not the other way around. In other words, the infrastructure here isn't tied to how the Finn dataflow compiler itself implements lowering or HLS ops or anything else. And you might actually find this useful for exploring DNN compilation independently. There's three key parts to this core infrastructure, which includes a wrapper around ONNX protobufs for easier manipulation, a structured way of defining and executing custom ONNX ops, and similarly, a structured way of manipulating ONNX via graph transformations. There are also various other utilities here, for instance, functions for executing custom Verilog as part of ONNX custom ops with PyVerilator, and various other goodies that are useful in general for this kind of work. To bring all of this together, let's have a look at what a Finn end-to-end flow actually looks like using a flow diagram to illustrate. So we'll start off with a trained quantized neural network in brevitas, which we export to an ONNX description consisting of these higher level ONNX layers. From there, we'll go into a sequence of transformations in the Finn compiler, which will first streamline the ONNX description to simplify it, then convert it each ONNX node to its HLS equivalent as implemented by finn-hlslib. And at this point, we have this graph of HLS layers that we can actually adjust the folding factors for to actually suit our performance and FPGA resource requirements. Once all of that is done, the Finn compiler is going to generate Vivado IPs for each layer and then stitch them together in Vivado IPI. And then this resulting design can be either integrated manually into a larger IP integrator design or put into an appropriate shell to get a PYNQ compatible bit file and a Python driver. In parallel to all of this, we can verify what the compiler has generated at various points by running Python, C++, or RTL simulations as part of the provided functionality. So that concludes our grand tour of the Finn stack. I hope this gave you some ideas on where to find what information. And with that, I'm going to hand over to Zaid to tell you more about the Finn community.
Thanks a lot, Yaman. Let me share my slide then. Sharing. So do you see the slides, guys? All right, good. So welcome, everybody. Thank you all for being here. In this talk, I would like to discuss the community that's being built around the Finn framework to be able to actually create more and more applications and also be able to bring together multiple different partners to support and benefit from this effort. So basically, this is a call from us to community building. If you look at the existing work that has been done so far with Finn by the community, we see that the GitHub repository has been started by more than 1,300 participants that are contributing or following this repository. We also see that the publications that we have published for the Finn framework have had more than 600 citations so far in the past couple of years that the Finn framework has been active. So there are many other users that are using Finn at the moment, and we would like to build this community together and bring together more and more people to be able to use it and also benefit from it. To give an example of what kind of activities at the moment that are, or partners that are using Finn, I'm dividing the different contributions into 4 different parts. So there are contributions to the Finn framework itself, building the framework and helping build the framework for various other new application domains and also optimizing it. There are a number of partners that are using the Finn framework either in research, or some partners are using it in the industry, building solutions, industrial solutions. And we also have partners using Finn in education. So there are very diverse partners that are using Finn in various different domains. Was giving a couple of examples on partners that are actually using Finn for their use cases or helping us build with Finn. So we have, for example, Heidelberg University and Delft University of Technology, who are actually actively building and contributing to the Finn framework itself, enabling others to use it in various different applications. We have a couple of partners that are actually using Finn in research. We're talking, for example, about the European Space Agency, the Fraunhofer Institute, CERN, and HLS for ML, all communities that are actually participating, using Finn to be able to apply some of their research in the field. There are a couple of industrial partners like Daimler and Thales that are using Finn in industrial applications. And there are a couple of other companies that are using Finn as well that will be announced in the coming months. In terms of education, as Michaela already mentioned in her part of the talk, there are a couple of universities that are already using Finn for classes, for example, Stanford, UNC Charlotte, and NTNU, and a number of others that are actually either already using Finn or engaged gradually in introducing Finn to introduce students to using hardware design for machine learning networks. Now with this, I would like to give you examples of how community engagement looks like. And with this, I would like to invite 2 contributors to the Finn framework. One from Heidelberg University, Hendrik Boras, who is building a tool chain for parallelism and pruning in Finn. And I would like to invite Jacoba Petri-Koenig and Martijn de Rooij from NICEF and TU Delft to tell us about an application that they have been using Finn to build for low latency pipeline for detecting gravitational waves. First, we start with Hendrik to discuss his contributions to the framework. Please, Hendrik, go ahead.
Yeah, thank you very much, Zaid, for the nice introduction. So what I would like to talk about here is basically one of the first steps within Finn to going towards parallel transformations and parallelizing the toolchain itself. So basically what I contributed here in one of the first parts of my master's thesis was to parallelize some of the transformations within Finn. So some of the work that needs to be done, as example, the synthesis of different layers can be done on individual nodes. And this is what we're using here. So basically what I contributed was a parallel transformation-based class. And this then leads to a per layer parallelization that one can use here. And it leads then to very significant time savings, especially for large networks. So on the right side here, you see a timing plot for an end-to-end flow from ONNX network to the final bit file. And this is here shown for different numbers of workers. And with the parallelization that's now within Finn, the synthesis time or the end-to-end time here goes down from about an hour to just a little bit under half an hour. So quite significant for especially development and testing with Finn. And the nice thing here is that this scales also with the size of the network. So for example, for the ResNet networks that are coming up and for the mobile net, this is really significant for easing up the build flow. Okay, let's go to the next slide. Yeah, on another side, I'm currently working on a bit more research-focused topic. So basically looking into bringing structured pruning to Finn. And the idea here is that through the resource savings that one can achieve through the pruning, that one can then run higher bit width networks. So basically, one can here trade kind of sparsity against bit width in activations and in weights. And as you can see here on the left side, for one of our pruning approaches, we have quite nice savings in the DRAM section, so in the memory section, and this can then be exploited here on the right side to run networks that have this higher quantizations. And this example here is actually on an embedded device, again, for a VGG-like network. And yeah, we're quite excited to see where this leads in terms of accuracy and throughput, so how this trades with each other. And as I said, just still an active research topic. So yeah, excited to see where we go there.
All right. Thanks a lot, Hendrik, for the contribution about how you can actually improve Finn for others to be able to use it in their applications. And this brings us to the talk from Jacoba about actually using Finn for a specific application domain for gravitational wave detection. Jacoba, take it off.
Thank you, Zaid. I would like to present you a project we did together with the National Institute for Subatomic Physics in Amsterdam, also called NICEF. The department we did the collaboration with is working on gravitational waves detection. Specialized and highly sensitive measurement tools are necessary for detecting these waves. In the setup from NICEF, a Michelson laser interferometer is used. The Michelson interferometer has multiple mirrors that have to be kept in a stable position in a so-called suspended state to keep the measurement going. Normally, trained staff ensures that the mirrors remain in the correct position, but since the measurement should also work when no one is available, NICEF want to have an automated control loop to take care of this. Using first a machine learning algorithm, the correction of the mirror position is determined, then a control system can adjust the mirrors. The timing and fast reaction time is essential in this setup because currently the control system needs to be working on 10 kilohertz or higher to keep the mirrors in position and not let them drift off. This would mean that the CNN only has 0.1 milliseconds to obtain the result for the correction of the mirrors. Next slide, please. Our part in the project was to analyze how the CNN can be implemented to fulfill the tight latency constraints. We decided to use Finn because it generates dataflow-style accelerators for FPGAs, in which you have more control over the latency. Additionally, Finn has multiple options available for the user to optimize the hardware accelerator for special constraints. One essential characteristic in the custom parallelization of each layer, which lets the user directly influence the latency, throughput, and resource utilization. We analyzed the existing end-to-end networks in Finn to find out if we can reach our goal. Next slide, please. Here you can see our results for one of the convolutional networks in Finn. On the x-axis, you can see the amount of parallelization, and on the y-axis, the latency in milliseconds. The blue line marks our 0.1 millisecond goal. The parallelization is done per layer, so depending on which layer is optimized, you see more or less improvement per step. By continuously increasing the parallelization, we are able to find a point that achieves the wanted latency of 0.1 milliseconds for the neural network. The resource utilization of this point can be seen in the bar chart above, in which you can see that from the supported boards in Finn, it is possible to implement this network with the latency, with the reach latency on the ZZU104 board or a bigger board. Thank you.
All right, thanks a lot, Jacoba, for your talk. Basically, this brings us to the end of our discussion about the community efforts. And with this, I would like, again, to call on you guys attending this tutorial to join us. We have a number of different ways that you guys can help build the community and support and contribute to the Finn framework. We have our GitHub channel for communication. So we have the link here. You can see it on the slides, Xilinx-Finn/community. And then you can contact me, Zaid Lars, you can contact Jacoba, and you can contact Yaman as well. And the emails are here on the slide to be able actually to communicate with us and we can actually define activities for you guys and specific contributions to work on. With this, I would like to say we're supposed to open a Q&A session now and a 10 minutes break, if I remember correctly. I don't know what the plan would be now. In any case, if you have any questions, please put them in the chat or Q&A button at the bottom of the Zoom window, so that we can see if we can answer them for you either now or later on. And I would like to ask Yaman if there is any plan or when the actual sessions for the training would go.
Yeah, let's give a brief update on that. First of all, thank you very much, Saeed, for introducing us to all the wonderful things that the Finn community does. Unfortunately, our fallback plan to bring back the other half of the instances that we haven't been able to spawn has also failed. So you should have now gotten one of two emails, either giving you the access details for the instances that we were able to create, or our deepest apologies, and that you'll be given priority for the rerun of the tutorial in 1 month's time. Once again, really sorry. This is something that is totally out of control. We've been trying to fix it for hours now, and no go. With regards to the timing, I think we should give our audience to ask questions for let's say about 5 minutes, and then we should move over to the hands-on session.
All right, so it's a mixed break and Q&A session. Basically, everybody who is available has the opportunity to ask questions or go and grab a drink before the hands-on session starts. I already saw a number of questions actually coming up during the presentation, questions about where the quantization is being used, whether it's in the forward pass or in the back propagation.
Yes. So maybe I can actually take that one while people think of new questions or take their breaks. So I think that question was from Olaf. I saw it briefly in the chat, and then we lost the previous session. So let's not lose that question. The story here isn't actually about quantizing the gradients or quantizing any part of the backpropagation part. In fact, when we're training quantized neural networks with brevitas, this is what's called a variant of fake quantization in TensorFlow. So everything is actually floating point, right? There are special techniques that we're applying, including using straight-through estimators to actually propagate through the non-derivable parts of the functions. All of the goal is really to obtain a network which at inference time can run with pure integer data paths. So there isn't any quantization going on the backpropagation or training side, if that helps.
All right. I hope that answers the question to Olaf. I see a couple of questions coming in. One question coming from Rajiv. He says, has there been any analysis on usage on GANs, encoders, like questions, or I guess he means GAN networks?
Yes, I can also take this one actually. Definitely for autoencoders, right? There has been successful case studies using Finn. They are unfortunately internal, so I can't actually disclose them. But I can say at least the kind of anomaly detection autoencoders you would use. We've successfully quantized those with Finn and actually generated hardware for them. As for GANs, I don't think we've actually ever built one. I'm thinking of there's been a community contribution on that side, but not one that I actually know of.
Yeah, so I think it depends on how you're using GANs, basically. So GANs mainly relate to the training phase, right? When you have an encoder and you have a decoder and they compete with each other to be able to build a network that is very accurate. I think once you have that network trained, then using the GANs actually is practically the same way for inference as other networks.
Yep, so to phrase that slightly differently, I don't know of any GANs that have integer on the forward pass while being trained. That's what I meant.
All right, so we have a couple of other questions coming in. We have a question from Erling saying, what are the main reasons for using HLS instead of HDLs for the Finn library? can you achieve the same performance with HLS description?
Good question. So the answer is yes and no. So the reason why we've sort of primarily went with HLS is if we want to introduce new layer types, that is a lot easier to do in HLS than it is in HDL. And we do want to be a little bit agile when it comes to thin compiler and library development. We have found that HLS takes us most of the way. It doesn't quite get us to the same performance as RTL. Therefore, I'll just leave it at this. I'll say watch this space. There may be a mix of more RTL and HLS components in the near future.
I see. Good. Thanks a lot. Other question coming in from Wong. He says that does Finn support other deep learning frameworks such as TensorFlow if they train a quantized neural network using TensorFlow and export it to ONNX model? Can they use Finn to generate the bit stream?
So there is no theoretical blocker for this. There is a practical one in the sense that we don't have a TensorFlow front end at the moment, right? So the first requirement being sort of using something like QKeras to actually get quantized training. But even if you do your quantized training with QKeras at the moment, we don't have a front end towards Finn at the moment. Again, I'll just say watch this space because this may actually change in the near future without making too many announcements here. But let's say for now, no. In the near future, maybe.
Lots of good questions, and they are very relevant for actual development. So, guys, these are important questions. These are very important candidates also for collaborations. So we move on to a question from an attendee saying whether using a dataflow model for a neural network, what do we do if the graph is too big? Because the network is big, that doesn't fit on the FPGA.
Right. I think I'll take this one as well. I hope I'm not sort of other panelists, please chime up if you actually want to answer something. But,
if you have the answers, that would be great. I mean, the panelists can chime in as well if they can contribute something extra as well.
I would just suggest that we start with the hands-on part now because it's getting quite late. Okay.
Then why don't we answer this one? And then I would ask the rest of the questions, if you could actually either ask them in the Clouder community room on FPGA, or even better, the Gitter channel that you got a link for the Finn community. We have a Gitter channel where you can actually ask questions. I'll be more than happy to answer those. In fact, I'll actually just make a copy of all of these and I'll try to give more detailed answers on the Gitter channel.
Great. All right. So thanks a lot then, Yaman, for the answers, and thanks a lot for all the other panelists for being here. Thanks to Michaela, Hendrik, Jacoba, and all the other panelists that joined us. And I would like then to ask everybody to move on to the other session. There was one housekeeping question coming up from one attendee. If one didn't originally sign up for the hands-on session today, how they can sign up for this next session? Do we already have information about the next session?
So not in the sense that there's a concrete link that you can go to register, but I'd say this will be announced on Twitter, on the Gitter channel that I just shared a link to in the chat. So if you watch that particular part, we'll be posting an announcement about this soon.
Great. Then I'll take this back to you guys, Michaela and Yaman, to head it off further.
Thank you very much, Zaid. And I think we'll just stop here for the webinar part because we really need to move on to the hands-on part. Again, those of you that have received the access details should have received a separate Zoom link for the hands-on part itself. And we'll see you there in a minute. Thank you very much for joining, and hope to see you again in the real world soon when the pandemic is more under control with fewer technical problems.
Bye, guys.